Hello, this is my talk on PLLs and the PLL project. So this is through the Analog Club here at the University of Texas. And what is a clock? A clock is something that we take for granted, right? It's an infrastructure piece a lot like power, but there's a lot of details of clocks that can make a huge difference to the systems they go into, right? So you could have a system be degraded by maybe 20% of its performance if the clock technology isn't appropriate, or if it's not as good as it could be. So let's look at some of the details that makes a clock. So first of all, the clock has to be detectable, right? You have to be able to tell the difference between up and down. And the clock has to be accurate, which is to say that when we design a clock for a frequency, it actually operates at that frequency, right? And then we want the clock to be precise. We measure this in something called phase noise, but what we're basically saying is that the frequency of operation will actually vary over the operation of the clock. And then dynamics, right? We want the clock to start pretty much whenever it has power. And some systems want a flexible clock, right? We want a clock that operates at 80 megahertz, 120 megahertz, maybe 400 megahertz, right? We don't want a lot of power go into making this clock. If it's something we're taking for granted, we don't want it to be a huge load on the system. And then, can the clock be integrated, right? Does it all fit on a chip? Or does it need external components? And reliable, in this context, when I say reliable, I'm basically saying, does it need a really stable voltage source? And then, is the clock cheap and small, right? This goes into, again, do we need external components, but also the area of the clock, right? Even if the clock can be integrated onto a single chip, if you have a clock take up a fifth of your area for your chip, then that may be unreasonable. So I want to start our discussion of clocks with the atomic clock. So this is a feedback loop which uses some type of either transmitter or laser to excite atoms. And we're wanting to excite the atoms to their frequency of maximum absorption. And when that exciter is reaching the frequency of maximum absorber, then that's when the detector will have the maximum amount of input. And then we're using that detector output to change the frequency of the quartz crystal, which is creating the excitation. And so the oscillator will actually change its frequency in order to find the maximum absorption of the atoms. Now it turns out that atomic clocks are integratable, right? Barely. This is a very large chip, quote unquote. At 35 grams, it has a few problems though. For instance, it's not very dynamic. Having to wait 3 minutes for your clock to start is unreasonable for many systems. The operating temperature is shallow, right? So this can never go onto a vehicle, for instance. The frequency is only 10 megahertz, and then it doesn't have a perfect output, right? Again, we measure precision in something called phase noise. And usually the trade-off for phase noise is power. But actually, because of the laser within this unit that does the excitation of the atoms, you're actually having a huge overhead on power, but you're really not seeing any benefit in the phase noise for that power loss. And lastly, it's $1,500, right? This is not going into a lot of products at all. Okay, let's move on from the electrochemical clock to the mechanical electrical clock. Crystal oscillators. Testing, 1, 2, 3. Alright. So, crystals can actually give us the clock technology that's in most of our devices. So how do crystals work? Well, they're a mechanical oscillator that has some coupling to the electric domain. And this is called the piezoelectric effect. So we're able to take a string mass damper system and turn that into something that looks like an LCR system. So there's a certain law, right, which says for some force you have some strain and vice versa. And then if you look at the Young's modulus, which is basically the relationship there on a micro scale, and the density of quartz, then you end up with a mass spring jet
damper system that has a resonant frequency given by the Young's modulus divided by the density distributed over the length of the crystal. It turns out that you actually end up with another factor of 2 in here because the lattice is pulling and pushing. But this gives you a rough estimate for the frequency of the crystals. And then you have some dampening. And it turns out that the dampening is actually based off of the area of the crystal. So if you make a smaller and smaller cut of crystal, then you're going to end up with more and more resistance, basically, in your circuit. And it turns out that the LCRs you see here aren't exactly what it would be in the mechanical domain versus the electrical domain, because, again, there's this electromechanical coupling in the piezoelectric effect. But the good news is that the frequency is the same, right? Because it's what's called a linear coupling. So from one domain to the other domain, it's just scaling by a constant. And so frequency is the same when you scale by a constant, but you're going to end up with a different damping factor. And then the last thing you have here is the cuts of the crystal, right? So what you want the crystal to be is you want the crystal to have the same frequency across a lot of temperatures. And a really popular cut here is this CT cut, this 38-degree cut. What this does is it helps compensate the crystal off of normal operating range for a lot of products. And so you'll go from maybe negative 10C to 85C. And that's what that cut is really good at. Because quartz in particular is really well compensated where it doesn't have a lot of temperature variation with frequency. Between like 0 degrees C and 50 degrees C, but these cuts make them much more stable. All right, now that you have a crystal, how do you actually get an oscillator? So back in World War I, when Armstrong was making the radio in the foxholes, you had Pierce, which is the namesake of our club. He was at UT, and then he went to Harvard. And while he was at Harvard, he made the first oscillators that were using quartz crystals. And so this oscillator actually came about 5 years younger, and it's a Kopitz oscillator. And the idea is that you have this LC network with this this electrical circuit. And this electrical circuit can be equivalent to this negative resistor and this capacitance. And so if you put that in series with your crystal, you're able to cancel the R we saw on the previous slide. And that allows the L and the C to resonate, and you'll thermally build up energy, and it'll start to get to an oscillator. And then the oscillation frequency is given by that LC network, and then we have to worry about a little bit of the circuit capacitance here as well. But usually data sheets for crystals will tell you to make this small compared to the C of the crystal. That way you don't have to care about it. So what is crystal technology like? Right? What's out there for this kind of stuff? So what you see here is that there's some tolerance. This is the frequency tolerance, right? This is how accurate the clock is, right? And it's given in parts per million. So the 10 pp for this 25 megahertz crystal means that that frequency is going to vary from device to device by 250 hertz, right? So in the context of 25 megahertz, that's not a lot, right? It's pretty stable. Now, frequency stability is actually talking about the variation across temperature, right? So for the rated temperature of this device, it's going to have that much variation across that temperature. And so it turns out that this device is rated from negative 10C to 85C. And so it's only varying by 10 parts per million again across that temperature. And then you have the ESR, right? In the electrical domain, how much resistance do you have, right? So when you have your circuit that drives your crystal, how much resistance do you have to conquer in order to get it to oscillate? And these are fairly cheap, right? It's able to get within all of its manufacturing within a decent price. And again, when we talk about manufacturing these crystals, we're talking about the height of the crystal, right? And then we're talking about how well to make that 38-degree cut across the crystal edge. Then, if you try to move to a crystal that's, an order of magnitude faster, like 216 megahertz, you're going to buy into a lot of stuff. So by making the crystal 10 times faster, that means you have to make the cut 10 times shorter, right? It's got to be 10 times shorter, and you still want to have that same accuracy, right? So you're paying it for your manufacturing, right? So because you can't make the crystal quite as nice at that scale, your tolerance is going to go up. In the same way, you're going to run into problems where you can't make the CT cuts as evenly. And so your frequency stability across temperature also goes down. And then another thing is that crystals are what's called bulk acoustic waves. And so there's a wave that's mechanical going through the crystal and bouncing back out. And that's what you're resonating, right? Is the wave is going through your crystal and back out. And so it turns out that as you increase frequency, that damping becomes higher and higher. And so your ESR is going to go up as well. And then because you have all of this tolerance that you're trying to dig for, even though you're asking for 10 times more, your price is going up by 15x, right? So you're really paying for it. Now, as a different technology that's out there, rather than these bulk acoustic wave resonators, is surface acoustic wave resonators, right? And that's this last object over here. So they're able to get much, much higher frequencies, and what they're paying for is that they're making these devices on top of the piezoelectric material rather than the piezoelectric material itself being the resonator. So what that means is that the electrical structure is actually lithography, right? It's made like a chip on top of the crystal. And then that means, though, that you're injecting many more errors, right? We're not very good at making geometries on chips, right? So you're injecting a lot more tolerance error into these geometries when you do that. So the tolerance of your frequency is higher. And then your frequency stability, right? Like I said, the quartz crystal is really well compensated across our everyday temperatures, like 0C through 50C, very generous, but that's a good temperature range for electronics. Now, other piezoelectric materials are not so well compensated, and so they're going to have a bunch of frequency variation across temperature that way. And it's hard to make those cuts again to compensate for that. So we're still developing that kind of technology. And then your ESR, right, because you're right in the surface of it, you don't have that attenuation through the whole bulk of the material. And so you're able to get much better ESRs actually. And then the other thing that's helping with the ESR is that quartz actually doesn't have a very good coupling for the electrical to the mechanical domain, right? So you can choose piezoelectric materials that have much better constants for that. We have a professor here, Rushen Liu, who does a fair amount of research that way. And so this is an article on his state-of-the-art of that. All right, before I move on to the PLL itself, do you have any questions? Crystal clear, huh? All right. So, with what you saw, right, the atomic clock is 10 megahertz, and the crystals are maybe comfortable around 25 megahertz, right? That's a very common crystal. How do we get to our clock speeds, right? How do we get to gigahertz, right? Some people need to terahertz, right? How do we do that with crystals or atomic clocks? And it turns out that there's an electronic device that we can make called a phase lock loop. That's what this PLL is. And it lets us turn that slow clock into a fast clock. So how does it do that? So you have a detector. This is just like the atomic clock, right? Instead of having an atom be your reference frequency, you're having an external clock, right? This might be your crystal, might be your atomic clock. And then you're feeding back a local oscillator, right? So you have some oscillator, and you're detecting the differences between that and your reference. And then you're feeding back that detection information back to your oscillator, right? And you're basically changing that oscillation frequency in order to minimize the error between those two. And so your output frequency for that oscillator will basically match your input frequency, which is great. Now, we're not really interested in making a mirror. We want something that's different. So how do we get from a mirror to something that's faster? So feedback tells us from 302 and some other classes that we have something that's our loop function, right? So we go from our output here, we have a feedback pin to this guy, and that's just a voltage divider, right? So we're getting some function of the output back here at the feedback pin. And then we're comparing that against our input, and we're trying to minimize the error between these two, right? So this is a voltage domain feedback system, and what we see is that if this term is big compared to 1, right? So we have our voltage divider times the gain of our amplifier plus 1. If this term is big, then that means that the relationship just becomes the gain times this thing. And then we have this thing in the numerator already. So all we're left with is this thing, right? All we're left with is 1 over h. And so that's exactly what we want for the PLL as well. So instead of using a voltage divider in the feedback path, we're using what's called a frequency divider, right? So we have some frequency output here, and instead of feeding back that frequency, we want to feed back something that's n times slower, right? And so this device is doing that, right? So now the feedback frequency will equal the reference frequency, and then on the other side, the output frequency will actually be n times that, right? And so that's how you actually end up getting higher frequency at your output. Now, it turns out the detector is a little bit more complicated than that. And so this is everything in phase domain. So you still have your output frequency is n times your reference frequency. And now you have what's called a phase frequency detector attached to a charge pump. And that's going to some type of filter. And then for the VCO, the voltage control oscillator, I've written it as constant over S. And S is an integrator, right? This is in phase domain or pulse domain. You have some integration, and that's how you're modeling that VCO. So it turns out that a little bit challenging the concept, but something that makes this much easier to understand if you go back to it is that phase is the integration of frequency, right? If you have a sine wave, what's going to be inside that? You have some omega t plus phi, right? And then, what happens if phi varies with t, right? What if it's linear, right? If it has some thing we'll call f1 times t, and that equals phi, right? Well, then this whole thing just becomes omega plus f1 times t, right? And so if you integrate this now, right, then, or if you differentiate this, right, then your t goes away, right? If you differentiate what's inside of the cosine. And so this term phi is actually the integral of frequency. A little rushed, but I really recommend this book by Zadar Zabi. He just published a CMOS PLL book. So if this is really interesting to you, it's a great read. Some of y'all have read Zabi books before. He's a good writer. So with all that, I'm going to go into some of these components real quick. So the thing that determines how good a PLL usually is the VCO. The voltage control oscillator is kind of the core of your PLL. And this book determines how much precision you can get out of PLL, right? This is kind of determining how big that precision curve is. And then it's making a lot of the trade-offs we talked about, right? If you want something that's really precise, you can trade a lot of area and go for a VCO that looks like this guy, where it's an LC VCO, right? It turns out that inductors are very hard to make on chips though, right? So that's how you get your huge areas out of PLLs, is trying to make an inductor on a chip. Or it can be an external component, right? Again, you're paying for an external component then. And then a very common VCO is what's called a ring oscillator. So actually, if you put three inverters like this, they'll start oscillating. And so that's a very common way. And what you can do is you can decrease the voltage from their supply lines, and that will make the oscillator go down in frequency. And then again, you have this relationship here, which is the output phase is the proportional control line voltage in here, right? That's all that is. All right, how about the divider, right? How do you get an electronic that takes a input clock and makes an output clock just slower, right? So it turns out, y'all done this a lot. This is a flip-flop. Flip-flop, if you have the output frequency go to the clock line, right? You have one clock cycle. It makes the output become the inversion of the last output, right? So QD is being fed the input. So this is the previous output. It's being fed back into here. So one clock edge makes it update this. The second clock edge doesn't, right? So by missing every other clock edge, now you have half the number of bits on the output, right? And so now you have a clock that's half the speed. And it turns out you can make a bunch of circuits like this, right? Where you have n number of events at your input, and they only have one event at the output. And that's the whole game you play with dividers, is how do I make a digital electronic, which gives me only one change in output for every x changes or n changes in the input. And so it's another linear proportion for your frequency effects. All right, and then the phase frequency detector. This is important because you don't want to be locked in the right phase, but the wrong frequency, right? And vice versa. You can tolerate a lot of variations if you're able to lock the exact frequency of your input. So in this case, this is another 2 flip-flops and then a reset signal. So how this works is that if clock B is, for instance, your VCO frequency or your divided frequency, and clock A is your reference, imagine for a second, like here, where clock A is to arrive before clock B. That means that there's some phase error here in favor of the reference. And now that we have now that we have some A here, right? This QA is going to be pulsed, right? It's going to be on until this reset is going to shut down this B flip-flop. And that reset only goes on when the VCO clock arrives, right? So it's when this clock goes high and this clock goes high. Does both QA and QB go high? And then, and only then, does this reset signal get sent, and QA and QB both go down, right? So what we're looking for here is something that tells the difference between when did the clocks arrive, right? And by having the difference between when the clocks arrive, we're able to calculate the error that that generates. All right, and so basically, this phase frequency detector makes a pulse for the difference between the two clocks, right? And that pulse is going to tell us how we're supposed to move the needle, how we're supposed to move the oscillator. All right, and the way that you turn pulses into that control line voltage is this charge pump. So this charge pump, based off the signals from QA or QB, will either drag up or drag down the capacitor voltage, right? So there's some current going in or out of the capacitor, and that voltage will basically take the oscillator down or up frequency, right? So if the control line is going up, that might mean that the oscillator is going the other direction, right? If the control line is going up, maybe the oscillator needs to get lower, right? In order to meet the requirements, right? In order to minimize the error of the phase frequency detector. So you can build these with current mirrors, and so Jim Giles wrote an article for us on current mirrors. But basically, it takes the error signals from the phase and frequency detector, and you see here is the current from these two things, right? I1 and I2 is IP, and then the capacitor, right? In a previous slide, I called this the loop filter, but really you're just looking for something that does an integration, right? You're summing together all the pulses to make your error voltage, right? And so that's what this S is. So now that you know the components, you have a loop filter, which has this integration. You have your VCO, which represents another integration. So PLLs are second-order systems. And because of that, you have second-order system dynamics, which means that you want this all to be stable. So you'll choose a frequency, a natural frequency for this PLL, and you'll choose a damping in order to make sure it's stable. And this natural frequency of the PLL basically says how fast the PLL can run. And then you have this factor of n here, which represents, you want to multiply frequency, right? And so this is how you get that multiplied by frequency. And so that's good, right? Because this transfer function represents the reference to output transfer. And so we have our factor of n here that we want. Alrighty, that's the really blistering pace what a PLL is. How do you use one? So here's some applications that are interesting. It turns out that the PLLs we want for radios don't want to multiply by n. They want to multiply it by some number that gives us our output frequency. Now, the way we're going to do that is what's called a fractional n loop. And the idea is that you have an average divide ratio that represents what the frequency you want at your output. So in this case, right, we're spending 90% of our time dividing by 10, right? So we get one event for every 10 outputs of your VCO. And then 10% of your time, you're spending at a division of 11, right? So every 10 cycles, we add another cycle. So it turns out that you get a multiplication of 10.1 at your output here. Now, that feels kind of weird, right? I'm getting a frequency of 10, and I'm getting a frequency of 11x, right? And somehow that averaged out, right? It turns out that you want this event to happen at a much faster time than our PLL transform, right? So you want to switch between those two quickly in comparison to omega n, right? And that's the game. Now, another game you play is that you don't have to fit all of that randomness that comes from that, right? That noise you generate by going from 10 to 11. You don't have to put that into a linear line. You can move all that noise to somewhere else in the frequency. And this is a similar way to how oversampling works in ADCs and DACs. And so they use that technique here to visually shape the noise away from the loop edge. All right. Another thing you can use a PLL for is a mixer, right? You don't need a mixer, you can use a PLL. So the idea here is that you have a line that controls the frequency, right? It's the voltage control line. So what you can do is you can have a signal that feeds into that line. And this example in particular is disabling the charge pump and enabling the signal, right? So it'll lock the loop to get to the frequency you want to transmit at. Then it'll let the other signal come in. It will wiggle that frequency. And then after sending so many bits of signal, you'll go back and make sure that the loop takes you back to your signal you're transmitting at. And so if you play the game right though, and your noise fits inside the band of the bandpass there, which is what that node ends up being, is a bandpass filter, then you don't even need this enable disable cycle. You can just send something like audio information straight through. And then the last application I want to talk about today is you don't even need a clock. So Ethernet, for instance, has these differential pairs, but these differential pairs, they don't come with ground, and Ethernet is digital data, right? It's ones and zeros. But you may have worked with UART, SPI, I2C, and all these standards come with like a data line and a clock line, right? So Ethernet does not, right? You have to do something called clock recovery, right? Somehow you have to dig the clock out of the data. And so what this electronic does is it basically, you set the bandwidth of the PLL so low that it doesn't even see the data. All I can see is the clock that data is writing on, that data is being changed on. And so this PLL is used in order to make sure that you don't have to send data and clock. You can just send data in Ethernet. And there's a lot of other standards that use it as well. All right. So that's all I have as far as PLLs go. If you're interested in getting hands-on, I have a project for you. So, I like projects with PCBs, right? Sometimes it makes the world a little less complicated. PCB is a mechanical support for electrical connections, and here's what it looks like. So this is a pillow that you can make. I have it in E2 next door if you want to see it. And this is the schematic view with down here, but here is also the board design so we can see all the wiring as well. All right, any questions? It's kind of an advanced topic, so I appreciate y'all. Again, if this is something that you're ever told to design, right? Okay, first of all, you can go read my article on it, right? And secondly, you can go read Masali's book. It was published last year and really helped me with the project. All right, well, thank y'all.
Thank you.